All right, good morning, everybody. It is our great pleasure this morning to have John Miller from Duke University, who is an actual statistician, to talk to us about, to give us an introduction to Bayesian analysis. Then we're going to have a coffee break, followed by a hands-on session. Take it away, John. Thank you.
Thank you so much. It's really a great pleasure for me to be here today doing this presentation. And yeah, I said my name is John Miller. I'm a PhD student in the statistics department at Duke University. And so today we're just going to have a quick overview of some of the practical aspects of doing Bayesian analysis and kind of why it might be useful and kind of get into the weeds a little bit. And then after a break, we'll get into more hands-on kind of session. But without further ado, let's get into it. So the first thing we're going to do here is kind of introduce this whole paradigm of Bayesian statistics. And so we're going to talk about, well, what is a forward problem, and what is an inverse problem, and how can we use Bayes' rule to kind of to solve inverse problems, which is something we often care about. So what is a forward problem? Well, in many cases, so in physics, we'll have some kind of theoretical description of how some process works. So this can be governed by PDEs, or in very rare cases, it could become some simple set of equations that can govern some system. And then these relationships work from some set of inputs, so we'll call these model parameters. So some kind of settings that reflect some state of the world that will kind of govern how the system will evolve from some the static point from which the system will evolve, perhaps. And then if you have some model that runs forward, there's going to be some kind of output at the end. There's some kind of numerical result, like if we're seeing how heat transfers along like a metal bar or something, we're going to get, well, what is the temperature at this particular point on that bar that we care about, maybe? So that could be one of our outputs. So to summarize in a single question, the forward problem is asking the question of, well, what are the outputs from some model for a given set of parameters? If we have our physics knowledge and we have a model that we feel good about, well, this is a fairly straightforward thing to do. I mean, there's plenty of complexities, but it's kind of known how to approach this. The other question we call the inverse problem, where we have outputs from some kind of experiment, and we have some theoretical model of how the system works, and we kind of want to use this experimental data, use it with the model to kind of back out what the model parameters would be that kind of generated the data that we saw. And so our physical models that we use, or not even just in physics, just all over the place, mathematical models that describe systems are generally not easily invertible equations. It's not like a line where we can just kind of take the reciprocal of the slope and we're good. So just straightforwardly taking the inverse here isn't something that's possible. So we need some way of kind of addressing this type of problem, where we have a complicated forward process and we want to kind of back out what produced what we saw. And so what this may look like is, if our observables have some kind of inherent noise to them, we have some kind of distribution that we see on our data, on our experimental data. And this kind of what we want to back out of that is kind of a probability distribution over the space of parameters, and kind of, you want to kind of nail down where we think the parameter might be. But in many cases, we're not going to be able to, get a single point estimate where we can say 100% confidence that this is the parameter value associated with the outputs that we saw. So there's always going, in these types of problems, there's always going to be some level of uncertainty that we're going to have to just be okay with. And so, like I said, we have some probability distribution over our observables, And we're going to hopefully from that get a distribution over the parameters. And so one very powerful tool, very powerful statistical tool that we have comes through this Bayesian paradigm of statistics, which is kind of all stems from this very simple result in probability theory, which is is Bayes' rule, which I'm sure many people may have heard of this before. And so let's say, to put this in its simplest form, if you have two binary events, event A and event B. What Bayes' rule essentially does, it allows us to switch the direction of conditioning. And by that, I mean, conditioning, well, probability of event A given that B has happened. And maybe if we know that, we want probability that event B happens given that we already know A happened. Or in this case, we're kind of showing the opposite. So you read for anyone who's unfamiliar, you read the pipe as like given. So if you have kind of the marginal probability of both the events and one of the conditional probabilities, you can get the other one. And so as we'll see in a minute, this can kind of feed into this setting of inverse problems. But we'll get to that in a second. But just to go through like a very simple, tangible example of Bayes' rule in action, let's say we know that 40% of all rainy days will have a cloudy morning. And in this particular city of interest, 10% of days are rainy, 20% of days are cloudy. And then the question is cloudy today? What's the probability of rain? And so we can fit this into the language of Bayes' rule just by, event A, we'll call it rain. Event B, we'll call having a cloudy morning. And then, 40% of all rainy days have cloudy mornings. Okay, well then, given that it's rainy, 40% chance of clouds, 10% chance of rain, 20% chance of clouds. And then we want to flip this direction of conditioning. We just plug everything into Bayes' rule and we get a nice answer there, nice and simply. And so now the question is, how do we use this kind of idea in solving, real inverse problems in physics? And so our goal, again, is to learn model parameters, which are unknown ahead of time, from some experimental observables Y. And so this Bayesian paradigm of data analysis is going to have, two main ingredients. One is your prior distribution. So we'll write this as pi of theta. And so this is a probability distribution which captures where we think the parameters might be before we look at data. So just based on prior knowledge of some sort, how does that, where might our parameters be? So you could say we're unsure, so we're assuming they're kind of uniform over some acceptable range, or maybe we want to have a more peaked prior distribution saying that, okay, maybe here in the middle, we think there's going to be, there's a higher chance that it's around here than maybe out on the sides of your acceptable range. So there are many choices of how you can choose a prior distribution, but that's something that we need here. And the other piece we need is what we call the likelihood. And so the likelihood, so f of y given theta, this is a function which describes the probability or probability density for observing a particular value of y conditional on a particular value of theta. And then we can fit these pieces into Bayes' rule just as before with binary events. Now you can just fit these things in here. And the piece that we're trying to get out of this is this what's called the posterior distribution. So after observing data, how do we update our beliefs about where our parameter is? And so really what's happening here is your likelihood is kind of talking with your prior distribution, and you kind of get somewhere in between the two. And that's kind of where we end up after we look at our data. And so I just want to stop here just to see if there's any questions before I move on, just to make sure we're kind of good on this kind of basic framework. So I'll just stop for a second. Well, then if we're all clear,
There's
then
someone, hang on, there's someone
Okay.
typing in
Okay.
Slack real quick, and
Okay,
I think let's give them just a second.
sure.
Or now I think they're still typing. Do you want to just unmute and ask your question? How can I be sure that my prior distribution is highly precise or unbiased?
So in general, you know, there is a certain degree in which your choice of prior distribution introduces bias, because, you know, obviously before seeing data, we don't know what you know, what the value of the parameter is going to be. So it always has to, in a certain sense, it's a bit of a subjective choice. And but what I think the important thing to note is, if you are, you know, don't have a strong degree of belief about where your parameters should be ahead of time, there are ways to choose a prior which is kind of minimally informative, such that it'll have a kind of minimal impact on the results of you know, what the posterior distribution looks like. Perhaps in certain settings, like choosing a just totally flat prior will kind of be that non-informative option. And the other thing is, if you have enough data, in most cases, the influence of the prior will really wane as you get more and more data. So it becomes less of an issue. And I guess with that, that means in the smaller data setting, you do need to be kind of careful about what you pick. But I guess to answer it in a sentence is, unfortunately, you can never be sure that you've picked the right prior, but something you can always do is some degree of sensitivity analysis. And we'll see a little bit of this in the hands-on session, is that, you know, if you try a couple different priors and kind of see how results look, and if you're kind of getting the same conclusion regardless of your prior choice or over a range of prior choices, then you're probably, you know, you're probably safe. Which I know this is kind of not a totally satisfactory answer, but unfortunately in this paradigm, we have to live with the fact that we need to make that kind of choice. And that kind of having to make that kind of choice is akin to in any, you know, in any statistics setting. Well, you have to posit some probability model for how your data is generated. So whether part of that is the prior distribution, or even if it's just the form of a model, assuming linear regression, assuming you know, Poisson, GLM, anything like that, you're still making kind of assumptions about the form of the data. And so there's always room for, you know, things to be wrong about the modeling assumptions we're making. But, you know, we have to see it as a kind of useful tool that kind of gets us closer to where we want to be. But does that answer your question to a good enough degree?
I think so. Thank you.
Okay, great. And then in that case, if there are no other questions at this time, then I'll continue on. All right, let's get back into it. So as we were saying before, you know, you have prior distribution, likelihood, you smush them together, and you get your posterior distribution. And so let's again just look at the form of the posterior here, you know, likelihood times prior divided by this integral here. And so we call this integral normalizing constant because it, you know, dividing by it makes it so our posterior distribution integrates to 1, which is something you need for a probability distribution. The potential issue is that especially if theta is really high dimensional, or pi if theta is really weird distribution, or f is kind of weird shapes. It's going to be hard to actually, calculate this integral. In general, you're not going to be able to calculate it. And so, you may ask, what do you do with that? Well, if I can't calculate this integral, how can I kind of get my posterior distribution? Thankfully, the major the major algorithms used for Bayesian inference, which rely on sampling from the posterior distribution rather than just calculating its value at different points. Well, these sampling algorithms don't require us to calculate this normalizing constant. So we're able to kind of proceed just by knowing the posterior distribution up to proportionality. And so that proportionality piece is just, the two components we talked about before, likelihood and prior. So we don't need to know the normalizing constant. And so now that we've kind of gone over the basics of this setting, let's get a little more into how does one actually do Bayesian parameter estimation. So we're going to start with a very simple example. So here we're assuming that our data come from the following model, which is, we have some parameter theta, and our observations are simply that parameter theta plus some normally distributed noise. And what we're going to do here is, well, okay, we need a prior distribution. So here, something that often makes sense in this kind of setting is to assume that for a prior distribution on theta to be normally distributed also. And then, well, the likelihood is probability of observing our data given a known value of theta. Well, if we look back at our model for the data here, what is it saying? If theta were a fixed value, all this is just a normally distributed random variable with mean theta. So that's what our likelihood will be in this case. And so this expression here is simply the Gaussian likelihood. And we don't, since we only care about things up to proportionality, we don't need the standard Gaussian normalizing constant, the 1/√2 pi thing. So this is our likelihood, this is our prior. And then to get the posterior distribution, we simply multiply these things together. And once we do a little bit of algebra, we see that our posterior distribution on theta is also still normally distributed, just with an updated mean and variance term. And so if we want to do some sort of parameter estimation, or we want to get some kind of summary about our posterior distribution, we know how to sample from normal distributions. And since we know the mean and variance, this is fairly straightforward for us to get whatever kind of summaries or information we need about this posterior distribution. We can do our parameter estimation that way. Great. But then let's say that we don't believe that theta, we don't want to use a normal distribution for the prior distribution of theta. Let's say we want to use a more general odd-shaped prior. Well, in this setting, in this case, the posterior distribution is not something that we're going to be able to write down in closed form and write as a kind of one of the standard known probability distributions. And so we can't directly sample from it. And so you may ask, then how do we sample from it? Well, we rely on a class of algorithms known as Markov chain Monte Carlo algorithms, where we use these algorithms essentially allow us to kind of sample from arbitrary probability distributions, and the arbitrary probability distribution that we use in this case would be our posterior. And so we design a Markov chain which allows us to effectively sample. And so the way that this works is to first you just start with you just have to initialize the algorithm somewhere. So what we're trying to do is start at a point and create a Markov chain which allows us to kind of move across the distribution. And so each state that the Markov chain visits we'll consider to be a sample from our target distribution. And a little theory tells us that this particular algorithm that we're going to go through, the Markov chain that that this distribution follows, will have stationary distribution equal to our target posterior distribution. And so that's why this whole thing works. So what we do first is we just need to initialize somewhere. And so a convenient way to do this is by drawing theta not from theta 0 from its prior distribution. So we just draw points. And then at each point, we need to kind of propose a new point to look next, a new point to sample. And so we're just going to choose what we call a proposal distribution. So given that I'm here, where do I go next with some probability? So we sample, and so ideally your proposal distribution should be something which is a known distribution or something which is very easy to sample from. And so here in this case, we jump into the left a little bit. And then now that we have our proposed points, we either decide to accept it or reject it. And here, and we accept with probability equal to this ratio. So the minimum of 1 or this term here. And I mentioned previously that we don't need to know the normalizing constants in order to do this kind of sampling. And here, if you look at this ratio, you can kind of see why. Because if I have the posterior at 1 point of our distribution at our new proposal point, and on the top and the bottom, we have our posterior at the old value of theta. Well, if I'm dividing, and both of these terms have the normalizing constant in it, well, it cancels out, so I don't need to know it. So I can, and it's something which, because it doesn't depend on theta, now I can do the sampling without having to calculate that potentially nasty integral. And so by repeating this process, repeating steps 2 and 3, we're able to get samples for this distribution. And so this is a trace plot. So this is just simply taking our values of theta that we draw from this algorithm and kind of just plotting them as a time series. And what we might do is, because if we just initialize the sampler at some random points according to our prior distribution, but as kind of alluded to in the question earlier, well, what if your prior is kind of way off from where the posterior is going to be, or even just the particular sample you got isn't really reflective of the distribution? So what we want to do is kind of wait for the Markov chain to kind of converge to where it needs to be. So if I'm here and the distribution is more like around here, well, it'll take a little time to converge, but the theory of Markov chains tell us that we will converge to kind of the meat of the distribution. So we call this burn-in, where you kind of throw out the first initial samples while you're waiting for the chain to kind of get to where you want it to be. So you might throw that bit out. And then another thing that we really want, we want our samples from this algorithm to kind of resemble IID, so identically and independent identically distributed samples from our target distribution. But clearly, by the fact that we're using this proposal distribution, which might be centered at our current point, you can imagine that there's going to be some degree of correlation between the points drawn by this procedure. And depending on the particular likelihood, depending on the particular prior we use, depending on the particular choice of proposal distribution, we're going to have varying degrees of correlation between samples in this chain. And so if that's an issue for your particular application, which it often is, one thing you can do is to simply do what we call thinning, where you only keep every m steps. So you only, every so often you keep a sample, then you keep the sample moving. The idea being that as we move farther apart in time, that correlation between samples is going to kind of fade. And so we're getting something that's closer to independent samples from our target distribution. And of course, you can do like a histogram of this plot and see what the actual posterior distribution looks like for your parameter of interest. And so again, I'm going to stop here because I know I just went through a lot and went through the Metropolis Hastings and everything. So I just want to give everyone a second to breathe and make sure we're all feeling good about this, and give a chance for questions here.
All right, there's two people who are typing. Although, all right, there we go. Javier says, I'm a bit lost on the convergence aspect of the posterior you were talking about. Can you repeat that, please?
So yeah, what I was mentioning is not convergence of a posterior, but convergence of your sampler to your posterior distribution. So let's just look at, if we look at here, let's say, let's say for instance that this sampling we're seeing here is reflective of our true posterior distribution. But maybe, our first sample that we draw from in our theta zero is kind of way off. Maybe theta zero is like 2 or something. So it's kind of way off from the mean of the distribution. The theory we have about Markov chain Monte Carlo tells us that as we sample more and more points, the stationary the distribution of points that we draw from this algorithm will converge to the true posterior distribution. So the first few points we sample might not really resemble this distribution that we care about, that we want to sample from. So that's why we often throw out the first, sometimes even throw out the first half of the samples that we draw, because we want to make sure that there's enough time for the samples that we're drawing by this process to resemble the true distribution we want to sample from. So I hope that's clear. If not, I can expand a little more.
He says, thank you, that helps.
Great. And then there was another question, or?
Whomever was typing didn't type it all the way in. So, of course, if you would like to ask a question, do speak up now or type it quick. Otherwise, please proceed. Thank you.
Great. Thank you. Yes, let's move on. And so what I described is what Markov chain Monte Carlo algorithm known as Metropolis Hastings. And that's kind of one of that's kind of the basic framework for MCMC. It's kind of the first thing you'll learn when you study this area. But of course, there are other more sophisticated MCMC algorithms which give us often better performance. And by better performance, what I mean is faster convergence. And so what I was saying before is it's going to be a lot quicker, that you're a lot sooner in the sampling process that your samples will start to resemble draws from your target distribution, and then have better mixing, we call it. And so mixing roughly means that your samples kind of adequately and efficiently explore the distribution that you're trying to sample from. So you're kind of getting samples from all pieces of the distribution. You're not getting stuck in one place. Like, for example, in this trace plot, if you're having bad mixing, you might see that like just a flat line at certain points if you get kind of stuck in some weird region of the space, and you're kind of like, or if you see like oscillation, like weird oscillation, not like fast oscillation like this. And so you're gonna, the end result of having poor mixing will be your samples aren't really accurately reflecting your posterior, which is bad.
So there's a question from Nikhil. What if there is more than one combination of right parameters as posterior?
Well, it's so if there's more than one combination of right parameter. So your posterior distribution that we're sampling from, of course, can be like very high dimensional. It's not just always a one-dimensional thing. And so you're trying to draw from the joint distribution of parameters, which means there can, of course, be some correlation between them, and there usually is. And so, if you have some pair of parameters that kind of agree with each other, of course, there can be multiple pairwise relationships between the parameters that work. So you're not just finding a single fixed value for anything. It's always, there's always going to be kind of multiple plausible combinations of parameters, just by nature of the fact that we're treating things as random here. So we're getting like a distribution over where our parameters might be, instead of like a point estimate.
Thank you. And someone was about to jump. Nikhil is responding. He says, "All right." And then there was someone about to type another question. If you do have another question, type it, and I will jump in, or you can yourself.
Anyone, feel free to just unmute yourself and ask questions yourself if you want. Like I am totally fine being interrupted. I just want to make sure that everyone is kind of on board with where we're going, and making sure everyone's following along. So at any time, please interrupt with questions. Happy to answer. But as I'm saying, you have these more sophisticated MCMC algorithms. One very popular and widely used method is what's known as Hamiltonian Monte Carlo. And essentially what this is it makes analogies to Hamiltonian dynamics in order to get a really good proposal distribution for Metropolis Hastings. And so with this algorithm, you tend to see you tend to see lower autocorrelation between your samples. So your samples more resemble independent draws, and you tend to converge to your target distribution a little faster. And of course, that's not always the case, but as this tends to work well as a kind of general black box tool. And if in a lot of the kind of more popular softwares for this, like Stan is one of the big software packages in the Bayesian world. It uses a variance of Hamiltonian Monte Carlo. And if you're interested in reading more about this, or just about MCMC in general, I'd refer you to this MCMC handbook. There's some great stuff in there. So it's a cool read. And I'm not going to go into the details of these other methods, but there are just to kind of illustrate that there's a lot out there of techniques here. One would be it's called affine invariance. It uses like an ensemble of samplers performing transformations to give you a better performance. And then in cases where your posterior distribution is multimodal, in standard, you might want to look at something like parallel tempered MCMC, because if you think, okay, well, the way that and like the standard Metropolis Hastings works is you're kind of trying to you accept proposals from high density regions more often than you do from low density regions. And so what happens if you have these two modes of your distribution that are kind of far apart from one another, it might be hard to traverse from one mode to another, and so you might get stuck in one of them. And so parallel tempered MCMC tries to get around this problem of dealing with multimodal distributions. So these are great, both great things to look into, but we won't be able to get into the details of these now. But I encourage you to take a look through these. And so now we've gone through all this machinery. We've discussed basic sampling algorithms. So now let's get into actually doing some parameter estimation here with a more realistic observation model. So before,
Sorry, I'm going to jump in. There was
Okay.
another question on the Slack, so that this one, he apologizes in advance that it's long. So on that last slide with the first 50 states, are you collecting your sample distribution for the posterior, and then whichever algorithm gives you faster convergence for the first 50 states is promising of a better estimate for input parameters?
So yeah, let's see. So yeah, so the way it works is you toss out your first however many samples you thing of your markup chain, and then you get the remaining states visited by your markup chain or your samples. And so what you'll do is you'll collect those and then treat these as like an empirical distribution over your parameter. Um, and as for like uh does faster convergence necessarily mean better performance and kind of better overall, more faithful representation of your target posterior? It depends, which I know is never a great answer, but I think so. Generally, fast convergence is tends to be a good sign, but there are other things to look at as well. And so one thing you want to kind of look at is just, once you converge, how does your mixing look? And so the general advice you get is that you want your trace plot, and this is just kind of like a very heuristic way of looking at it. You want the trace plot to look like a fuzzy caterpillar. That's the thing that people tell you, where you want this kind of like rapid traversal of your distribution. So that's the main thing you really want to look for. Or because if you saw, this fuzzy caterpillar shape, but then it was kind of oscillating slowly with these faster, smaller oscillations, but the broad shape looks almost like sinusoidal. That's not something you want, because then you're seeing you're slowly traversing the distribution, and that can be indicative of some issues. And so there are a number. If you want to look at the performance of MCMC algorithms, there are a number of kind of performance metrics that you can look at, and different MCMC diagnostics. So there's two of those you might want to look at, are like the GWEC statistic and the R hat value. If you look those up for MCMC, that'll kind of get you into the right space of looking for that kind of stuff. But diagnosing your results from MCMC, sometimes it takes a little bit of care, and you have to be kind of careful, but generally, fast convergence is a good sign, but it's not everything. So I hope that answers that question.
Thank you. And if you guys, let me there was something in this. Yes, thank you.
Great. So now let's get back into it with doing parameter estimation in a more realistic observation model that might match what we're really doing in practice. So before, we had our observable was simply the sum of our parameter and observation noise, so Gaussian noise. Now what we're saying is our observable is the some arbitrary function of our parameters plus some observation noise. And so in our use cases, this eta of theta here will be our computer model that we're interested in working with. And so then the idea is we match experimental data with some computer simulator, and we use those together to do some sort of parameter estimation. And so here, as before, well, if eta is just a deterministic function, well, then we can just our likelihood is still Gaussian, still normally distributed, so we can just fit this eta of theta into the normal likelihood here, and then we sample from our posterior distribution using MCMC as before. So that's great. And so we've now had a way in which we can embed our computer model into MCMC. So now we can do our parameter estimation, right? Well, if eta for our computer model is something which can be evaluated very quickly for any given theta, well, then this works great. But as I'm sure many of you know, these computer simulations that we use in modern applications tend to be very expensive to evaluate. They either, they'll take a long time or a lot of compute power. So we're not going to be able to, just plug the simulator into this likelihood and just kind of go as before, because it would just take forever to run. Because every iteration of our MCMC requires us to evaluate this thing. But there is a solution, there is hope, and that is through what is known as model emulation. And so this is just to motivate what we're getting into, but I want to just stop, make sure everyone understands that why this is an issue. We need to, when doing MCMC, this likelihood needs to be evaluated every step. And so if the likelihood is expensive to evaluate, we're stuck. So we need to get it, we need a way around that. So that's what we're going to talk about now. And so we're going to go through, second, let me plug in my computer. We're going to go through kind of the the canonical model used for model emulation, which would be Gaussian process. And then we're going to talk about, in most settings, we don't just have one single observable, we have several. So how do we deal with, models that have multiple observables? And then we're going to kind of look at the whole Bayesian inference workflow. And so one way that we can speed up our simulations is via the use of model emulation. So the idea is this. So we have some expensive simulator, and so we can't afford to run it that many times. But we run it at a few carefully chosen sets of parameters. And so at each of those carefully chosen sets of parameters, we get all the associated outputs. And then what we do is we train a predictive model on that simulated data. The idea being that we're trying to predict the values that the simulator would take at a new value of theta. And so then when it comes time to evaluate our simulator at a new point that we haven't tested yet, instead of having to run the simulator again, which is very expensive, we can instead just make a prediction from our predictive model, which is going to be much faster and allows us to go through our whatever we need it for. In this case, evaluating our likelihood in our parameter estimation problem. But we're going to be able to do that a lot faster than just running the simulator again. And so just to show that here, well, we first generate some simulation data. So we'll call it 1 through m, different types driving this. And for convenience, we often assume that our parameters come on some unit hypercube with and so we just performing appropriate transformations. And then our outputs are very expensive, so we're going to try to there's two pieces of this prediction that we want. The first, we want to just predict. We just want a kind of prediction of what that output will actually be. We want a kind of a mean prediction. The other thing we want is to be able to quantify the uncertainty in our predictions. We want to know how certain we are, because I think that's important for kind of propagating uncertainty through our data analysis process. We don't want to act as if we're totally certain about the value this thing takes, especially since we're doing prediction here off a limited data set. And so in this image here, the dark line going through the center, that would represent our kind of point prediction. And then the football bubble shapes you see around this line kind of represents the relative level of uncertainty about the value the function takes, about the value the simulator takes at each of these new theta values. And so you can think of these uncertainty bounds as kind of like a confidence interval of the value that your simulator will take it at a given value of theta. And so the way we do this, the way we do a statistical model here is kind of akin to the Bayesian inference process as a whole, where now instead of assigning a prior to a particular parameter, we're assigning a prior to a prior stochastic process to our function. And in this setting, a stochastic process, you can think of it as simply a function. You can think, so we're saying we're assigning a prior over the space of functions. And so what we're assuming here is that our simulator, the relationship between parameter and outcome between theta and y, is some smooth function. And we're trying to learn what that smooth function is. And so in order to figure out what it is, we're going to assume that our function is the random outcome of some process, some stochastic process. And so we're going to assign a prior distribution over those potential outcomes. And then we're going to condition our data and we'll get a predictive model. So what we do is, in this image here, these might be potential outcomes from some random function generating process. And then,
sorry, there's a question from Kayron. Does adding another simulated point change the error estimates everywhere or just between the two closest simulation points?
Well, it will do it everywhere. And so we'll get into this a little bit later, but kind of the mechanism by which you're reducing your uncertainty at a point is it's distance based. So as your uncertainty, let's say there's two rightmost points. If I were to observe a point in the middle, you can think of it as kind of you're clamping down the football shape in the middle, and as you get farther away from a particular observed point, its impact on reducing uncertainty reduces. So you're getting the most reduction of uncertainty at the points where you observe the function, because there you're eliminating all uncertainty if we're saying our function is totally observed without noise. But usually there will be noise, but but you're reducing uncertainty globally, but that global reduction kind of tapers off with distance from your point that you're observing. And so here, this function that we're assuming a prior distribution, and so the way we kind of tamp down the shape of this thing, the way we go from a flat line or some random wiggly thing to this more defined shape is by conditioning on data. And so the particular function prior we use here is what's known as a Gaussian process. And many of you may have heard of Gaussian processes. They're very widely used in a lot of areas. People in machine learning use them all the time. A lot of people in astrophysics use these. A lot of people in engineering use these because they are a non-parametric model that is very flexible. And essentially what they are very smart interpolators. And that tends to be pretty useful. And so let's just go through what is the Gaussian process. So before we get into talking about mean function covariance functions, the basic assumption of a Gaussian process is that let's say I have some function going through this space. What I'm assuming is that if I were to take any finite number of points along that function, their joint distribution can be described as multivariate normal. So that is the Gaussian process assumption, that any point on my function, any pair of points is bivariate normal, however n points is n-variate multinormal. multivariate normal. And so this model is kind of parameterized by two pieces. One is a mean function, just to say, like, before sampling anything, where do I think this function will be on average? So what's the average function as produced by this random process? And then a covariance function, which is just to say how correlated are 2 points at different points in my process. And usually this is something which just monotonically decreases with distance. But there are exceptions to that, but generally that is what is done. So here we might say that in this particular case, we'll say that on average, this process produces a flat function, but then of course you see all different types of functions that are coming from the same thing. And then, so the relationship between theta 1 and theta 2 could look the function value of theta 1 and theta 2 could look very different depending on which random draw you get. So you need to condition on data so you can kind of figure out what that relationship is. So to show how this works point by point, here is our prior process before looking at any data, and you'll notice that we have just flat uncertainty across the whole space. But now as we collect data, at the point we collect data, now there's no uncertainty, and you'll see that near the point where we saw data, we see a greater reduction in uncertainty than we do farther away. But even, a little farther away, you can see that there's still some reduction in uncertainty. And then as we get more and more data, we get a better sense of what the shape of this function is. And we reduce uncertainty as we go along. So, we had this process which takes a random function, which generates a random function. And by conditioning on our observations, we kind of get a sense of what the pieces of the function that we haven't seen yet look like. And so that's the basic idea and how we fit this thing. And so I'll stop here for a second just to make sure we're all clear on Gaussian processes and how they work. So I'll just take a second.
I am not seeing anything in the chat or anyone typing.
Great.
If you have a question, chime in, please.
That was the time.
All right, thank you.
All right. If not, then let's keep getting into it. And so the very useful thing about Gaussian processes is that owing to certain facts about normal distributions, but multivariate normal distributions, we know that any points we want to predict at, we have a closed form answer for how to. I won't go into the details of this expression, but just know that we have a closed form answer for the value that we can of our predictions. And we also have a closed form answer for the variance at any given point along our function. So this is really useful for us because those are the two things we want. We want a point prediction and we want uncertainty quantification. So a Gaussian process gives us these in a very neat packaged form. So this is why people tend to use them a lot, because these closed form answers for mean and variance. And so often we will assume that that the mean of that this process has a constant prior mean function. So before we're conditioning on data, so that really means that the work being done by this model is really done through this correlation function. And so there are a few popular correlation functions in the literature. Probably the single most popular is what is known as the squared exponential kernel. And I'll point your attention to a couple different pieces of this that kind of give us a lot of flexibility in the types of shapes these random functions can take. One is this gamma variable out front, and this kind of represents like how minimum to maximum, what the total amount of oscillation or not oscillation, but so up and down of your function can be. And then you have these what we call length scale parameters within the exponential, and what these control are how smooth is your function in each direction. And so just by playing with these, we get a lot of flexibility in the types of relationships we're able to capture here. And there are also other popular kernels, which I won't get into the details of, but the matern is a very popular one, as well as a cubic correlation. And we're going to talk a little bit more about the practical fitting of GPs in our hands-on session a little later. And so let's talk about now. Okay, well, we know how to we have these emulators. Well, let's incorporate them into our inference pipeline, because that's the whole reason we have them. We don't want to just make a predictive model just to do prediction. The predictions are useful for something.
Sorry, there's a question in the chat. Could you please explain again what you mean by closed form?
So by closed form, I mean you can write it down as just say as a mathematical expression, where you how to describe closed form. So closed form is there is a mathematical equation that doesn't involve nasty integrals or some kind of iterative process, just like this is what it looks like. Whereas this is just like a matrix inverse operation that you're just it's a thing plus a couple other things multiplied together. So I guess there's not really a precise, is there a precise definition of it? But it essentially means it's something that's easy to write down, that doesn't require, if you were to compute all the objects written there, you wouldn't need to do like an additional like integration or kind of weird construction to get the thing. It's just readily available to you, which means it's something which can be efficiently calculated, or if you want to do some sort of optimization, it's easier to optimize this and have gradients available to you, and then having to estimate things. So it's just having something written out in a clean mathematical expression, we'll say.
Thank you. And I'd just like to point out there's about 15 minutes left before the scheduled break.
Yeah.
We can push it a little, but we don't want to eat too much into the hands-on.
Okay. Yeah. We should be fine. And so what we want to do is in our, as before, we had this expensive simulator in our model likelihood, in our likelihood for in the posterior. So what we want to do is replace that with our emulator, which is fast to evaluate. We want to do this. But is it as simple as just swapping them out? Well, no, because the emulator is something that we're kind of inferring probabilistically from data, so it itself has its own level of uncertainty. So we need to kind of make sure we're incorporating that predictive uncertainty into our inference problem, so that we're not being overconfident in our estimates. And the way our emulator, at any point we have some level of uncertainty associated with the emulator, and so we need to integrate that to likelihood. But it turns out that there's actually a fairly simple form to this addition of uncertainty, which is you simply add your predictive uncertainty to your kind of baseline experimental uncertainty, and then you're able to proceed as normal. So everything works out well there. And so we can use this modified posterior distribution, this one that uses our emulator instead of our simulator, to do our MCMC sampling. And so this is the key thing, that this allows us to do our parameter estimation even when we have this really expensive computer model. And this is enabled through this fast emulation. And so now let's talk about doing emulation with multiple observables. So in many problems, we're going to have some big number M of correlated observables. And correlation is kind of tough to deal with in general. So what we want to do is kind of reduce the dimensionality of our problem. So it would be great if we could take M, big number M, correlated observables and reduce down to some smaller number K of outputs, which of transformed outputs, which are independent from one another. And then if these things are independent, we can model them independently and do as we did before. So the method that we're going to use for this dimensionality reduction, which is something which is very widely used, is principal component analysis. And the one sentence summary of what this does is it kind of finds the directions in your data that have the maximum variation or which are maximally important, and kind of projects data onto these directions to give you kind of independent kind of transformed variables. So what we do is we take our observables, we do some kind of linear transformation to give us vectors which are orthogonal, which kind of span our data, which define our data, and we kind of order them by their variance in this projected space. And this notion of orthogonality that we get through doing these linear transformations translates into statistical independence, and that's what we want here. We want independence. And so to give an example of this, here is a very common test data set in machine learning, the iris data set, where you have these four-dimensional data, and there's three different classes. So those are the colors. But what you see if you look at these pairwise scatter plots, you see that there's some clear relationship between our variables. And so if we wanted to model each of these variables separately, well then, we might be out of luck. But thankfully, if we do principal component analysis, we can kind of disentangle these different dimensions in our data. So if you see here in the in this table of numbers, we see that just this four-dimensional data set can really be described almost perfectly. 90%, 96% of the variance in this data can be described using just 2 dimensions. So we're able to reduce from 4 dimensions to 2 in this case. So to make things computationally easier in modeling, let's say we only care about, we just throw out the 3rd and 4th dimension because they don't really give us that much information. We just take these first 2. And so here you can see just a plot of these first components, and you'll see of these 3 classes that are in our data set, we can already see some separation based on just these two components. So they kind of give us all the information we need about identifying these plants, for example. And so doing this kind of dimension reduction is often a useful tool for use in other downstream tasks like classification and emulation. And so how does that work in our setting? So we have n data points, n different data values we tested, and at each of those points we have m observables. So from that, we can get a sample covariance matrix to learn how these different observables are correlated to one another. And then we do an eigenvalue decomposition of this covariance matrix and sorting by the eigenvalues. We take the first k eigenvectors and just simply multiply by those eigenvectors to get our transformed principal components. So it's fairly simple to kind of do this kind of transformation. And the idea is just a little bit of math shows us that if this works out, these should be approximately independent from one another, which means we can model them independently. And so so not only have we taken m correlated things and disentangled them, we've also reduced the number of things we need to model. We've reduced from m to k, and then we can simply just train independent GPs on each of these. So now let's look at the whole Bayesian inference workflow. So what we do is we have our m observables. We do some sort of we do PCA to reduce our dimensionality and create k independent pseudo observables. We model each of these each of these principal components with the Gaussian process separately, because we can treat them as independently after we've done this dimension reduction. Then we can, from these transformed, these predicted values in this transform space, we simply do the inverse of this PCA transformation to reconstruct our full M predicted values. And so this is how we're then able to model M things which are correlated using the technology we've already discussed before in the session. And again, we just use these as we did before in our MCMC, where now we, instead of just a single observable, we have all M of these to deal with. And so the result of this is that we're able to do Bayesian inference and parameter estimation in these complicated, multi-observable, expensive simulator settings. So here's just an image from a 2021 work from JETSCAPE, just kind of showing for certain parameters in a problem, for each pairwise, each pair of parameters, you're having these different shapes that we're able to kind of parse out on how these parameters relate to one another. And that is the goal here. But that is all I've prepared. So I know I went a little fast through that last bit, just because we're running out of time. But if there are any questions, or if you want me to go back and clarify anything, feel free to ask at this point.
At the moment, there are no questions on Slack, but there's somebody was typing. Don't be shy. I think any question is welcome. So how can the PCA be reverted? How does one come up with additional parameters? I guess no information is lost. So some more comments on the principal component analysis, I think, would be nice. How can it be reverted? How does one come up with additional parameters?
Yeah, so you invert PCA just simply by taking the inverse of your transformation matrix, and then you kind of slap on the extra columns, and that so that's like a common thing that is done. So that's not a worry. Because, and if you are only there is, what I will say is that with the reconstruction, there is some loss of information, because this is a data compression technique, which means you can't store everything. And so if we're taking this, like in the iris example, we said 96% of the data, of the information in the data is really contained in the first 2 dimensions of our PCA. Well, that means if I'm only modeling those two principal components, I am throwing out some portion of the information.
Mm-hmm.
And so when I'm reconstructing, in this case, if I have this M dimensional thing and I'm only taking K dimensions, there is some amount of information that I am losing. So you could, in principle, do PCA, but keep all dimensions, just now knowing that each of my M things are independent from one another. And in cases where M is relatively small, that's a totally fine thing to do. The issue is when M is really large, the modeling overhead of modeling M independent things might be too much. So that's kind of where you kind of have to make this trade-off of computational feasibility and information loss. So that there will be a little bit of sacrifice you have to make there, but it's in many cases, it's not too detrimental to lose some information in doing this compression and reconstruction.
Okay, there's a follow-up question on what is the use for the extra parameters, and now why do you want to revert, or I assume invert, your PCA?
I'm not sure what you mean by extra parameters. but the reason you'd want to invert PCA, so you have, so let's kind of go with the pipeline. So you have your data in its normal form. You're doing this weird linear transformation, this PCA, to kind of, you're essentially rotating your data such that each of these observables in this transform space are independent from one another. And the reason we care about that is if you were just to, without doing any sort of transformation, try to model each component, each dimension of your observable, each observable separately with a separate process, by ignoring that correlation, you're really losing a lot of kind of model fidelity. You're losing the ability to accurately represent the thing you're trying to model because you're missing this very key component of it. But PCA, it tends to move, in the kind of theoretically like well-defined within this particular probabilistic model is defined, it makes things like perfectly independent. In practice, it will kind of make things mostly independent and move it in that direction, but it's never going to be perfectly independent, but it's enough of a thing such that by modeling these principal components separately, you're not really losing that much. And so that's what, perhaps what you're getting at by extra parameters is these principal components, that you're generating. And so the purpose of these is that they are independent from one another, so they can be modeled separately without much loss of accuracy. And then the reason you invert that is because we want to convert things back to the original space, because we're in our normal data space. We move into this transformed principal component space, but we want to transform back into our data space after doing prediction, so that we can fit things into our MCMC sampler.
Okay, at the moment I don't see any other. No, there's one more question. So maybe we make this the last question before the coffee break. So not eat too much into the hands-on session. Just trying to correlate your talk overall with what we do in general with our experimental data analysis. So basically, I can interpret the unfolding procedure, and thereby inverse of PCA implies a closure test. Okay, I don't know if you have comments on this.
Well, so I mean, a closure test is a bit of a different thing, because that would be, running, doing the whole inverse problem, based on just assuming that you're using your simulator as experimental data. So you could use these techniques within a closure test if you have multiple observables. But I wouldn't say this technology would be, this kind of processing is exclusive to doing something like that.
Okay, so yeah, I think it's not a sort of a very close correspondence there, but I mean, I have to say this workflow slide is, I think, it's very clear, and I've certainly learned from that. So maybe we'll take the coffee break now, and I think we should just try to be back at 10:30 to leave the full hour and a half for the hands-on session. So you have 11 minutes of a coffee break, should be enough. Back at 10:30.
All right. Thank you, everyone, and we'll be back in a bit.
It is being recorded.
Great. Okay, wonderful. Then, all right, as I was saying, what we're going to go through is doing a parameter estimation workflow using Gaussian process emulation. And so we're going to see how all these pieces fit together. So just to briefly summarize a little bit of what we went over, in Bayesian inference, we have some relationship between data that we observe and some parameter that we're interested in making inferences about. And so we make those inferences about the parameters through the calculation of the posterior distribution. So here's the form of that distribution where D is our data. Probability or density of theta given data is the likelihood times the prior over some normalizing constant. And as before, this normalizing constant is something that we don't actually need to calculate in practice. And that's a good thing because it's usually a very difficult thing to calculate. But we can avoid that altogether through using sampling. And so what our likelihood is, just to go over that again. Our likelihood function is, it's a density which describes the conditional probability of making some kind of observation, of making a particular observation conditional on a specific value of the parameter. So in general, this can be an arbitrarily complex relationship. For our simple setting today, because we want everything to be computationally very quick, we're just going to assume a simple linear relationship between our parameter and the output variable. But these methods are sufficiently general that does not need to be the case. But we're just doing that out of pure computational convenience today. And the other thing that tends to be an important feature of these inverse problems is this notion of having additional statistical error on top of our simulation. So if we have data that we observe, it's not always going to be perfectly noiseless, collected, completely precise. There's going to be some kind of error. And so we want to make sure that we can account for that error in our inference so that we're not, overconfident in our conclusions that we make. So here to express what our simulator model is in this particular setting, as I said before, so linear relationship. So y is just some scalar times our parameter plus some bias term, and then plus our experimental noise, our statistical error. So what we're going to do first is we're going to import a couple libraries. NumPy is just useful for kind of standard math operations in Python. Matplotlib, Seaborn is for plotting. And then GPy is a really great package for using Gaussian processes. It's very well done. There's a lot of great functionality there. So we'll be using that. We'll be using something from sklearn just to kind of pre-process data a little bit. MC is a great MCMC library which implements affine invariance sampling. So that's a great tool. We'll be using that. So let's first, we have a function here which defines our simulator model. So that kind of linear relationship we said. So it takes in some theta. We're just treating our intercept and slope as fixed. We're not worrying about those. And then we have some noise variance, or rather noise standard deviation in this case. So how much statistical error is there on top of the kind of baseline relationship that we're looking at here? And so we'll define that function where what it does is just calculates our point on the line and then just adds some noise. And so, in general, these simulators that we work with are going to be Oh, you want me to zoom in? Yes, I can do that. Now, is that a bit better? Okay, great. Sorry about that. So what we will do here is now we have this model, and so in general, our simulators that we're working with are going to be fairly slow, fairly computationally complex, and so we need to implement. We can't just directly do inference with our simulator model. So as we went through in the lecture portion, we need to build some kind of fast emulator. And so for our purposes, we are going to use a Gaussian process for our emulation. And these are great because they give us very easily accessible mean predictions, as well as, I guess, more importantly, they give us good uncertainty quantification on our predictions, which is something that we will need in order to actually incorporate them properly into the inference pipeline. And so these Gaussian processes are good for like non-parametric interpolation between our data points. And so since we're doing interpolation, we need to have a good, sample of points which fill up our parameter space, such that we're actually able to do good interpolation. Because, however smart your model is, if you don't have enough data, if your data doesn't reflect the whole space you care about, well, then it's not going to work well. So what we're going to do is choose an initial design, some set of points on which we train our emulator. And in practice, this is something that you get to control, because we're working with a simulator, so you get to pick the experimental design of data points that we're using to train this thing. So there's a very wide literature on how to design experiments, how to choose points to get good emulator performance. In this case, we're working with a one-dimensional parameter, and we are saying that our theta lies somewhere between 0 and 1 over pi. And so all we're going to do in this case, just for simplicity's sake, is kind of just pick a regularly spaced grid of points over over our design space. And so we're gonna observe our simulator at these points, and that of course comes with some noise. And so what we get is that we have our, I should really zoom out just so we get the whole graph. So what we get is, here's our observation. So the black dots represent the points we see. And then based on the uncertainty that we have, this is where the actual function could be at within anywhere within this range. And so this is our data that we've generated. And so now we're going to try, let's ask a couple of questions here. One, does it look like a linear model generated this data? So there's some deviation from that linear trend due to the noise that we see, but roughly you can kind of see that linear trend. Now, if we were to do something like we just go back a little bit and let's multiply the amount of noise in the problem by 10 and see what this thing looks like, suddenly you lose that shape. And so that's a really important this kind of side point, which is in doing any sort of data analysis, if the signal to noise ratio in your problem is too large, in certain cases it becomes difficult to parse things out, and so you can be really limited by that. In this case, with the kind of original level of noise, you can still see that shape, but you can see that the level of noise in your problem can really, one, change how difficult it is, and really, change what you actually see when you see the data. So noise can really obscure trends. Even in a simple model like this, having too much noise can really, get in the way of things. So I'm gonna stop here for a second, just to make sure we're all on the same page, make sure we're good with the setting, and we're all feeling good. So I'll pause for a second. I'll watch the chat.
No questions on Slack for the
that's-
moment, but
Okay.
let's see.
Yeah. Give 1 second just to. All right. Not seeing anything, so let's keep on moving here. So now, what we're
Hey,
going
John,
to.
you can also use the ask people to put the thumbs up or check mark or whatever to see if they're
Okay.
following along. Yeah.
Sure. Yeah. Okay.
Ask for
And
proof of
usually-
life.
Yeah. Yes. And waiting 1 second usually doesn't help when people are typing questions. Maybe we wait a
Sure.
minute. That might also help.
Yes. Okay. So yeah. All right. So yeah, we'll do that at the next point we stop. But right now, I will. Looks like there are no questions in the chat, and maybe we can get some thumbs up just to make sure we're all good. I'll wait to see that a little bit. Thumbs up. See a couple thumbs ups. But I'm not seeing questions. So people no thumbs up. Is that just you good, or I don't want to move on unless we're all feeling good. All right. Well, if there are no objections, then we'll keep moving with it. So the model we'll be using today is a Gaussian process, and these are there's a few links here that I encourage you to go through later and play with. One is just Wikipedia page on those, and then there are a couple widgets you can play with. There's this widget here which is really great. It kind of shows you how these things condition on data, as well as for a more detailed treatment. There's this famous book, Rasmussen Williams 2006, which is a great guide on Gaussian processes. So that's a really good read. Then for more descriptions of some popular kernel functions, I point you to this page here, and some more visual exploration. So these are all some great links just to look through. If you're curious and want to know more about Gaussian processes, I would say these are a good place to start. But for our purposes today, what we need is, as I mentioned in the lecture, our kernel and our mean function have some sort of we have some hyperparameters that need to be tuned. And the way that we're going to tune these in practice is through maximum likelihood. And so, as I said before, our observations can be seen when we assume a Gaussian process. Our observations take on a multivariate normal distribution. And so what that means is what we do is, and they take on a multivariate normal distribution, which with correlation matrix, with covariance matrix and mean, given by our particular hyperparameters at that point. So then what we can do is just learn those hyperparameters through maximum likelihood. So by optimizing this log likelihood here, we're able to get get good hyperparameters that describe our data well, that describe the level of smoothness and spread in our data. So we're going to do that here. And so there are two pieces to our kernel. Because remember, we have just the baseline. We're assuming that we have some function, some Gaussian process function, but then there's additional observation noise on top of it. So our kernel has two pieces. One, the kind of spatially dependent kernel that gives us correlation between observations, which will be our squared exponential kernel. And then there's this observation noise, this white noise kernel that gets added to it. So we're going to use a combination of these to build the model that we're positing for the data. And so this RBF kernel, that is the same as the squared exponential kernel, our white noise kernel here, and then we simply add them together. And so that'll get us what we need. And as is kind of common practice in a lot of out-of-the-box methods, we tend to get better performance when we scale our outputs to a unit range. Being asked to use a poll. Oh, here we go. Let's do. Before we start, let's do a little poll just to make sure we're all on the same page here. Okay, we got about half the people coming in. Okay. Waiting for a few more answers to come in, but it looks like a lot of us are feeling pretty good and feeling like we're catching up really soon. So I'll just give people a little more time to respond to this poll and to catch up, see how we're feeling. So those of us that aren't fully caught up yet, if I don't know if anyone is willing to has any questions or needs a point of clarification, please feel free to ask. It's like we have 70% response rate so far, and I'll give the people that said should be caught up in a minute. I'll give a little bit of time for us all to catch up here, and I'll just reiterate a little bit of the previous points. So assuming a Gaussian process model here implies that our simulation observations, so our training data rather, is distributed according to a multivariate normal distribution. And so because we have that distributional form of our data, we can then learn the tuning parameters for the Gaussian process. So our kernel parameters, in this case, because we're assuming a constant mean function, so just a mean zero. So we can just learn those kernel parameters through maximum likelihood. And so we can do that here by first we build our kernel by adding up this RBF kernel. So this square exponential kernel that we went over in lecture, plus this white noise kernel, because our data are seen with some kind of experimental noise. And so what we'll do before we fit our model is to scale our data appropriately just to get better performance. So zero mean unit variance. That tends to work very well in a lot of for out of the box. It tends to help with performance a little bit. And so now, thanks to this package GPy, it's actually very simple to train one of these models. Once we have our data, once we've scaled it appropriately, all we need to do is just run these 2 lines of code here. One just defines the model, and then one optimizes the likelihood. And so now we can see that we've learned all of our parameters here, where we have our different pieces of our kernel. So our variance for the different pieces of our kernel, the kernel length scale, and white noise variances. So now we have our model. So the next thing we need to do is actually construct a function for predicting from our model. So again, we need 2 things from this prediction. One is a point prediction, a mean prediction. And the other thing is we want the standard deviation of our prediction. And that's, those are both given to us by our Gaussian process posterior. So we're going to define these. And now what we're going to do is plot our performance of this model against the simulator, or against our training points rather. And we're going to see how that fits. So here is the model. So in the middle is our mean prediction. And then to the sides, we have varying levels of standard deviations away from that mean. And then we're plotting that with our simulation output. And so what we can see here is that our emulator does a fairly good job of capturing the relationship in this data. One thing you'll notice is that our underlying model here is just a linear model, right? But we see the shape that we're predicting is there's a slight non-linearity to it. And that's owing to the distortion from the statistical noise. And because there's noise, we're not going to perfectly capture, our relationship, but we seem to do a fairly good job of capturing it reasonably well. And in this case, it seems to be almost exact to a certain extent. Like we're getting pretty close to that linear relationship, just small deviation from it. And I would encourage everyone to come back at a later time and really play around with this just to see how changing the amount of data we have changes uncertainty, changes the shape of the prediction, how much noise noise to our observables, to our observations affects the shape of this learned function. How changing how points in our design space are spaced out, where they're put, how does that affect the shape of our function? So I think playing around with these will really give you an intuitive sense of how these emulators tend to work. So I think it's a really great exercise to go back and do that and just kind of test your intuition on these things. But at this point, I'll do another quick poll maybe, and just make sure we're all on board with this kind of basic setup of fitting the emulator and kind of seeing how it predicts against our observations. Looks like most of us are feeling pretty good so far. That's good. I'll give another few seconds here just to everyone to answer. Call it 15 seconds more. All right. Well, it looks like the people who are responding are feeling good, and everyone's feeling pretty good about where we are. So I'll just take one more second, and then again, I would encourage everyone to come back in the portions of this notebook where it says exercises. I think it can be really useful just to for building intuition to go through these things and kind of see how changing things will change our results. So I think that's probably a good thing to go through and do. But let's get back into it. So because our model is a interpolator, is training on our observation points, we would expect it to do pretty well at the points where where the model is trained. But we're using this thing to predict at points where we haven't checked before. So let's create a testing set, and then model. Let's look at our performance of our model on this testing set, and see how things look. So all we're doing is uniformly generating points in our design space, and we're generating observations from our linear model here, and we're going to see how they look. And I saw someone typing something, so I'll just wait a second. And so what we've done here is we are plotting our emulator prediction versus our pure linear model output. And so if points were to lie exactly on this line, that would mean that we would have perfect prediction. But here we're seeing some deviation from the line. We're not exactly on it. And that's kind of to be expected in this setting, just for the reason that, we have some level of just baseline randomness in the linear model output. So of course, if there's some randomness involved, we can't always predict perfectly just because there's not some static thing that we're trying to predict. So I would say that this level of match between our linear model output and our emulator output is probably pretty close to as good as we can expect in this case. And so we can ask, like, let's just try to get a better look at how this performance looks. So let's plot our model residuals and see if there's any sort of bias, any sort of systematic bias to these. And so here are what the residuals look like. Is there a error on the histogram? No. So it should be.
There's one question on Slack.
Yes, I'm seeing that.
Okay.
Yes. So no. So here, we're assuming that we're not assuming there's some fixed true theta yet. We're just trying to learn an emulator to learn the mapping between theta and y. And so we're looking at we're trying to predict y from theta at this point. And so what we're looking at is we want to be looking at that y hat minus theta, because we're trying to, for a particular theta, y hat minus y, because we're trying to learn the relationship between theta and y at this point. We're just right now we're not thinking about inference, we're not thinking about learning theta, we're just thinking about predicting y well from theta. Does that make sense? Oh, on the histogram, but on the histogram, yes, that is correct. That is a typo. Yes, I didn't notice that. So that should be this should be your distribution of residuals. Yes. And yeah, so this should be y hat minus theta right here. But if we're looking at this scatter plot, what we're seeing is that there is some. It looks, with a finite sample, there's always going to be like some level of bias, but there's but here it looks pretty good. It's like it looks like a pretty Gaussian spread. It looks like we're not seeing too much systematic bias in our prediction. Maybe you could argue that it's a little under predicting towards the middle of the range here, but I think overall these residuals look pretty good. It's not like we're, not more than you'd expect the level of noise we have in the problem. So now we have our fitted emulator. It seems to be performing well. So now let's get into performing some Bayesian inference. So our posterior distribution is the distribution of theta conditional on our data, given our experimental data. And so the way we can calculate that posterior is by knowing that it's proportional to our likelihood times a prior distribution. So in order to do this process, we need to choose a prior distribution. And so what we're going to do here is look at two different prior distributions, and we're going to kind of compare them to see what effect our choice of prior will have on our posterior distribution. So our two options that we're going to look at here is one which is very non-informative. So it is saying it is putting our prior belief, spacing it out evenly over our entire range. So to say that ahead of time, we have no, prior belief that's in one place versus another in our space, just, can be anywhere. And then the other prior is going to say that, it's going to have a peaked shape to say that there's a certain portion of the space in which we think our parameter is more likely to exist in. And so we're going to, and our peaked prior, what that actually is it's normal distribution truncated to within a certain range. And so we're going to plot these and see what they look like. And so, here are two different prior distributions. So the flat one, it spaces prior belief evenly over our design space. And the peaked prior here really puts a lot of weight towards the middle of this space. So it's really saying that ahead of time, we're fairly confident that it's within this center of this region. And so our final result should reflect that. And so the next thing, so now we have our prior. The next thing we need is to define a likelihood. So here, again, our likelihood is the conditional probability of observing our data given some fixed value of our parameters. So in this case, it is the conditional probability of seeing y given theta. And so it's common to believe that our likelihood here is multivariate normal. So Gaussian distribution is generally for fixed mean and variance, it maximizes informational entropy, which tends to mean that it's a fairly safe choice to use. And in this setting, it is kind of, it is the correct choice because we know what the model is. And so using a Gaussian likelihood is the right choice, but in general, you're not going to know that. But using a normal likelihood, assuming normally distributed noise on top of your simulator is the common practice. But it does vary on a case by case basis, but that tends to work in a lot of applications. But it is something you should consider on a case by case basis. I really want to emphasize that not everything is Gaussian. A lot of things tend to look sort of Gaussian, but not everything. And there are some pretty dramatic departures from Gaussianity, so be careful. But in this case, we are using a Gaussian likelihood. And so the question here, when we define this likelihood, we have our for a given theta, we can calculate the mean, and we do that by predicting from our emulator. And that's as before in the presentation, when you substitute our emulator into our predictive likelihood. So we're doing that here. And then as we kind of said in the presentation, you need to incorporate your kind of standard, your baseline experimental noise into this likelihood, but you also need to have your model uncertainty go into this. So you need to add those two together, and then we simply plug in the standard Gaussian likelihood formula here. And this will give us and we're taking the log of it, so we have our log likelihood here. And the important question to ask is, well, why does this variance here have variance in our likelihood have this particular form? Well, I'll type it out actually to mark down. So what we're assuming is that yi is equal to eta of theta plus epsilon. This is what we're assuming our noise model is, right? But the thing is, because we're estimating, we're replacing that with this. So we have this hat, and here it is fixed. No. But in this second case, we know that eta is actually normally distributed with some what we have is that now eta hat is a random quantity, right? So because eta hat is a random quantity and it's normally distributed, I'll flip this. There's another hat here, just sort of being precise. We know that this is normally, and so it's Gaussian, and we have Gaussian noise on top of it. So, well, when you add two normally distributed things together, the result is normally distributed and with added means and added variances. So that's why in this log likelihood, the variance is additive. So that's why it has that form. And I think it's important to go through that just to understand why. So we're essentially, by introducing the emulator, we're kind of in a way changing our observation model for the data. And so that implies, that we need to have this additive form of our variance. So here I'll stop again, just do another checkpoint just to make sure we're all good with all of this and all the kind of stuff we discussed so far before we move on to getting our posterior distribution. And the more people that can participate in the poll, I would appreciate it greatly. Just so I can make sure that we're all on the same page here and feeling good about everything. Looks like we had a lot of results. And then I'll there are a couple people that saying okay, so what is stuck? So people who say they are feeling stuck or lost, if you feel comfortable, could you please let me know what it is that is, I guess, where where I can help kind of provide some more color, some extra clarification. So now's the time to ask questions before we get more into the weeds on the putting things together and mixing everything into the parameter estimation piece. So those of you who are saying you're a little stuck, please ask a question about where you are, or I can just give another minute or so just for everyone to kind of catch up. Okay, it's like answers have stopped rolling in, but let's see. So just because we had a couple people there saying they were stuck, I'm gonna relaunch the poll and just let it run again. We're gonna see if those people that said they're catching up and just caught up, just because we've covered a lot. I apologize for the numerous polls, but it's an easy way for us to meet it, for us all to see that we're all doing good. Good. And give a little bit more time to catch up. And I'll just, kind of go back a little bit here. So here, we have our two pieces for Bayesian inference that are really important. One is we have some posterior distribution. We have some prior distribution. And so here we're gonna compare how our results look with one of these two prior distributions. So we're gonna use only one of these at a time. So one being a flat, less informative prior, and one being a more peaked informative prior. And then we have our Gaussian likelihood that goes with it. So our observation for our model for conditional probability of seeing our data given a particular parameter value. And so that is what our likelihood is. And it looks like we're mostly feeling pretty good now. So I think we can probably move on. And the posterior is proportional to the product of our likelihood and our prior, right? So then the log of the posterior is simply the sum of the log prior and log likelihood. And so we do that here. So because we have two different prior choices, we're going to have two different posterior distributions. And so we're going to have one posterior using this flat prior, one using this peaked prior, and then we're going to look at those a little later on and compare results. So that's that. And so now we do let's say we do some experiments and we get our data back. In this case, we only need to know the experimental data mean, just as the way things work out in this particular case. And the experimental data uncertainty, which we're saying matches our assumed uncertainty, just for simplicity's sake. So we have our experimental data means, and so this is very simple. In general, you may not have an analytic expression for your likelihood, or things can be very complicated or high dimensional. So we need a general tool set, and that general tool set is going to be Markov chain Monte Carlo. And so in our particular case here today, we're going to be using a package for Python called MC, which is a great Markov chain Monte Carlo package. And let's just go through this block of code a little bit just to see what's going on. So we know that our parameter in this case is just one dimensional. We're just estimating one single theta. So our dimension of the sampler is 1. We're going to have 20 parallel, MCMC runs going, and we're going to do our burn-in. So we're going to throw out the first 1,000 samples from our sampling while we wait for the sampler to converge to the stationary distribution, so to our posterior. And then after burn-in, we're going to do an additional 1,000 samples from our posterior, and that should give us enough to make whatever see the shape of the posterior. And then we're also going to, in an effort to reduce correlation between our samples, because we want them to resemble independent draws from our posterior, we're going to thin every 5 samples. So we're going to keep every 5 samples just to limit that correlation. And so with this package, we can give a starting guess to kind of hopefully start off our sampler in the right spot. So that's what we're going to do. We're just going to kind of randomly pick a point within our region. And so then what we're going to do is do our sampling here. So we'll sample from our posterior with using the flat prior. And then we are going to do our thinning and burn in and retain those samples. And then we're going to do the exact same thing, but using the peaked prior. And we'll see a little later is that we're going to get different results from those 2 different prior distributions. And so now let's run this sampling. And I'll stop again as I'm waiting for the sampling to run, to make sure we're all in a good spot. I'll do the poll again, and if there are any questions, please stop me, and I'm happy to answer anything, anything that could be unclear at this point. And this may take a little bit of time to run. Okay, looks like we need some time to catch up. For those of you who are saying that you need a little bit of time to catch up, is there anything I can help with? Are there any is there anything that's unclear that that I can help answer and help clear up for you? Feel free to unmute yourself and ask, or you drop messages in the Slack or in the Zoom chat, whatever. Happy to answer any questions this time. While you have people answering the poll here. Enable solid GPy. So if you run this through the Docker, it should have all the necessary packages installed. But perhaps it may be a little too late to install to get the whole Docker environment set up. But and if it is, and you're having trouble getting that installed, then this notebook is available on in the GitHub link. I'm gonna put the I'll put the GitHub link in the Zoom chat one more time. I'll even put it in the Slack channel, just so at a later time you can go through it. If you're having software install issues right now, you can go back and run through it then when maybe when you've been able to get that ironed out, or you can even just on the GitHub page, the notebook is there with everything run already. So you can see all the output from it. So yeah, there's a couple options there. But I'll pause just another second and just make sure there's no other questions before we move on and look at our results from our MCMC. I'm gonna wait. I'll wait like another 30 seconds or so. Then we can move on to the next portion of this. Yeah, so here, just to summarize what we've done so far, so we started off by generating training data for our Gaussian process emulator. Then we fit our emulator, and we kind of looked at how well a job that did at predicting across our sample space, and we saw that it did a pretty good job. There's some inherent noise in the problems, so you're never going to predict perfectly, but it seems to do a very good job at kind of representing the relationship here, representing the function. And so now we did that. Now we've said, okay, let's move on to doing inference. In this case, we're going to pick. We have two different prior distributions that we want to try out, and then those are paired with a likelihood function for our data, in which we are substituting our emulator for the true data generating model. And so then we fit that emulator into our likelihood, and then we use that likelihood, which is now fast to evaluate. And I mean, it's fast to evaluate before, but even if in a real setting where our simulator is really expensive, that would still be fast to evaluate, and we can do MCMC. As you saw here, like fairly quickly, we're able to sample from our posterior distribution, and we'll be able to plot these in just a second, and see how everything looks and get our posterior distribution on where we think our parameter might be. So there are a lot of things we can do. We're going to move on now. There are a lot of things we can do to kind of examine our MCMC results. And so probably the most common thing is what we showed in the lecture is to plot your trace plot. So to kind of treat your samples from your sampler as a time series and kind of see how those look. And there are also plenty of other MCMC diagnostics. There's a couple of links here I'd encourage you to check out. Those can give you some more metrics to look at. So here are what the trace plots look like in both of our prior distributions, and both of them don't seem to indicate any sort of issues. For both of them, we see that fuzzy caterpillar shape that we like to see. It looks like we're traversing the distribution fairly efficiently in both cases. But as you can see, even just from the trace plots, the posterior distribution we're getting from each of these is slightly different. And so there's going to be, it seems to be the case that these priors are having different influence on the posterior. So we'll examine that a little later. And so now what we're going to do is to plot these posteriors not as trace plots, but just as a normal density plot. And so now we're going to see what these look like. And so what kind of what we saw with the trace plot, there's a little bit of difference. Now you can see it very clearly that, there's a stark difference in what we're seeing from the posterior distribution based on our choice of prior here. And so this kind of tells you that your prior can have a lot of influence on the conclusions you make. So it's something which you should give a fair bit of consideration to. It's kind of it's a bit of an art to choose a proper prior. And when in doubt, I think the general practice is to choose something which is less informative, because if you have enough data, then your likelihood will overwhelm the prior. And so it kind of tends to be the case that you kind of want to, if you're maybe err towards the side of caution and having an uninformative prior, if you're not, if you don't know where it might be, unless you have very strong beliefs about how something will be. I'll wait for this question here pop up before we move on. You couldn't get how to exactly trace plots. Yeah, we'll go back to those. So a trace plot is, you can imagine when I'm sampling from my MCMC algorithm. This is to say, like, from one point to the next, I'm just drawing different samples from different parts of my my distribution. And so depending on your proposal distribution that you can choose, yes, there can be very rapid fluctuations, but that's kind of what you want, actually, because something that would be a bad outcome is if you have like really small movement from iteration to iteration. What that means is your samples are going to be very correlated to one another. So actually having rapid fluctuation is actually desirable, because it means you're traversing quickly, and your samples are more likely to resemble independent draws from that distribution rather than correlated draws that are right next to each other. But yeah, so this plot is from one point to the next. It's iteration 1, I sampled this point of my distribution. Iteration 2, I sampled here and here. So we're just looking at it over time to see if there's any sorts of patterns of that would be suggestive of strong autocorrelation or kind of pathological behavior of your sampler, which is getting stuck in one place. Because if I'm, for example, getting stuck in one very small region of my space, then I'm really overestimating the density of that region. And so that's negative, because then that's bad, because then that gives you kind of a skewed picture of what your posterior actually looks like. Is that clear?
Hi, John. Can you hear me?
Yes.
Sorry, it was taking a lot of time to type, so.
No worries. Yeah.
Yeah, I mean, so in that sense, what you just explained, if I consider like any peak overshooting at any value, I can also consider it to be a pathological behavior, right?
Oh, no. What do you mean by overshooting?
Like you have certain rapid fluctuations where like it overshoots to 0.3 and beyond, and let's say suddenly there is, I mean, at a certain point, it even goes beyond, and you would still consider it to be a rapid fluctuation behavior as others, or?
So well, it depends. So there's some type, in certain cases, you'll have what's called like, the chain will diverge, where, because for whatever reason or another, maybe your posterior distribution is ill-defined. Your chain might kind of run off to infinity, or like run off in weird places and not converge properly to its proper distribution. So that can certainly happen. But in these cases, for example, we're not seeing that kind of thing, where we're kind of shooting off like super far off and then returning a little bit, and then shooting far off. But it looks like we're kind of there's a certain area which we seem to be traversing, and we're kind of repeatedly traversing that area. And that's kind of what you want to see. This would be indicative of good mixing. We call it mixing, where it looks like there's something that we've converged to that looks like to be a somewhat stable thing, but we're rapidly traversing that stable thing. So I think that's probably the good way to put it. All right, great. In that case, we'll move on a little bit here. So here we have our plotted posterior distributions that we get different shapes based on the prior that we've chosen. And so let's look at these. They do differ. So what's different about them? One, you'll see their kind of midpoints is in different locations. The peaked prior, the midpoint of it is pretty close to where the posterior with the peaked prior is pretty close to where the prior is. So it's a very informative prior. It's not taking that much influence from the data in this case. Whereas we're seeing here, well, we had a flat prior, and it very clearly is not flat anymore. So we're seeing some, it's being more responsive to the data, and we're also seeing wider uncertainty because the prior is less concentrated. Your posterior will be a little less concentrated. It kind of propagates in that way. And something that I would encourage you to do is to play around with the experimental error on our measurements and see how that affects the shapes of these posterior distributions, and then play around with the parameters in the peaked prior, like how peaked it is, where it is, and see how that changes. And so we'll look at those things. And the one question that I'll give the answer to here is I think it's really important. So when we use a flat prior distribution, remember, so our posterior is proportional to likelihood times prior. So if we have a flat prior, what that means is our prior distribution is everywhere within our acceptable range proportional to 1. So it's some constant, which means our posterior distribution is then simply proportional to your likelihood. So then everything is given by likelihood. So that has particular consequences. So I think when you have a flat prior, your posterior and likelihood are proportional. So that's I guess this is a good fact to be aware of. And so now the next thing we're going to plot here is the posterior. It's what is known as the posterior predictive distribution. So the posterior distribution is after I've observed data, where do I now expect my parameter to be? So posterior predictive is one step beyond this, which is to say, given where I think the posterior, where my parameter is, where does that imply that my data should be? So more practically, that's to say, for every sample I draw from my posterior distribution, I'm going to then, for that fixed value of theta, I'm going to draw a value from Y's distribution, conditional on that value of theta. And so to say, well, what is the utility of looking at a posterior predictive distribution? And that would be to say, does the posterior distribution that my assumptions have resulted in, does the data generating distribution implied by that posterior match up with the reality of the data that I've seen? So it's kind of it's almost a bit of a sanity check to see if my model results kind of match with the data that I've observed. So let's plot that. So for every draw from our posterior, we're going to look at the predicted points based on based on our model. And so what we have is in green here. This is where our data is. Our data is at the center of that with some experimental error around it. And then this is the distribution on Y that our flat prior implies. And then in red here is the distribution on data that is implied by using the peaked prior. And you'll see that these are very different from one another. You'll notice that there's different degree of uncertainty, and there's centered in different locations. And so doing this kind of check, we see that while about half of the weight of this posterior predictive is kind of within the range of experimental noise of our true data, it seems that it's perhaps somehow off base from where reality is. So maybe that choice of prior is somehow maybe somehow insufficient. Whereas with our flat prior, since we're really relying more heavily on the data and less on our prior beliefs, we see that the center of this posterior predictive distribution seems to align well with our data that we have in the setting. And I know that the notion of posterior predictives can be a little confusing. So I'm just going to stop and do another poll just to make sure we're all on board here and answer any questions before we keep going here. I'll give a little bit more time because we have just a bit over half participation in the poll so far. But I'll give a little bit more time. And so those of you who are feeling a little stuck, if there's any clarification you need, please, I'd encourage you to ask, just because let's make sure we're all on the same page with all this stuff. I know this is something that was confusing to me when I first encountered it too. We'll give them a couple more seconds just for the poll. It looks like we're mostly feeling pretty good, which is good. And I'll just reiterate kind of the notion of what the posterior predictive is, because I think it's an important thing to go over. So it is, we have a question brewing in the chat. Saying while we're waiting for this question to come in. So yeah, posterior predictive is, supposing we have some posterior distribution, what is the distribution of Okay, so it seems better to use the uniform prior. Is this the case always? Okay. So no, I would say that uniform prior is not always necessarily the best case. For one, let's say that your parameter of interest doesn't just take values in a specified range, but over the entire real line. So in that case, well, one, if you were to use an improper prior, you'd either have to do one of two things. One, you have to truncate at over some range, which in some applications it may be fine to do that, but you're still kind of limiting the full expressiveness that you have. And then, or two, you can use a flat prior over the entire real line. And that's something which is known as a improper prior, because a probability distribution needs to integrate to 1 over the real line. Doing a flat line over the entire real line, well, of course, that integrates to infinity, so it's not a proper probability distribution. So sometimes it is okay to use improper priors. It's very common in the kind of Bayesian statistics literature. It's a well-studied thing, but you have to be very careful using them, because they can produce some very pathological behavior, which can create a lot of issues. So you should be like, sometimes uniform prior works if you're but not always. And then as for changing the mean of the Gaussian prior, again, that kind of goes to what your degree of prior knowledge about the problem is. Because if you have a really strong sense of where it should be, then by all means go ahead. But if you're trying to kind of just overfit to where you think it is, it may be hard ahead of time to know where it is. So if you're trying to pick a Gaussian prior, but you don't really know what it is, then you could run into some issues. Now there is a this area of known as, you can look this up, empirical Bayes, where you kind of use your data to inform your prior distribution, and that's kind of something which is really widely done too. So I would encourage you to look at that as well. But there's not a blanket answer as to is some prior always good. Now there is something which is a very useful tool, which is known as Jeffrey's prior, which is more of a kind of, you can think of it as a kind of general purpose non-informative prior, and it's not necessarily uniform. Because the thing about uniform priors is, if you do certain transformations on your parameters, which you may need to do, and in a non-informative prior in one parameterization could look very informative in like a certain transformation of your variables. So if you want to preserve some like kind of standard use case black box prior I can use that is kind of sort of non-informative, something like Jeffrey's prior, which is invariant, maintains a notion of non-informativeness across different parameterizations and transformations, that's probably a better thing to look at. But to say that there's I don't think any Bayesian statistician would say that there's like a one size fits all answer to priors. It's a complicated choice, unfortunately, but that's the nature of the beast. And then to look at so I was saying there's a print an image that may be looking okay. Posterior picture with flat priors. So I don't know what might be going on in that image there. If you change, I'm saying is, did you see did you change anything in any of the numbers in the file, or no? Then unfortunately right now I wouldn't know immediately what might be going on there. maybe one of the TAs. Okay. I believe we have one or two TAs currently on. Maybe if one of you could look into, maybe try to see what's going on there, just because are running a little short on time and I want to make sure we can get through everything. But so maybe yeah, it's an issue, but maybe it might help just to kind of follow along with what I'm doing on the screen, that if you're having these kind of weird results, then maybe the TAs can try to help you out. How about we do that? Just so we can get through everything. And then we can circle back at the end and try to maybe help you diagnose what's going on there. But the next thing we want to look at here is kind of just do some baseline validation, because what we are doing is we're doing a modified posterior that uses the emulator instead of the true simulator. So what we want to do is in this simple case, this is something which is feasible because our simulator is very fast to evaluate. So this is something that we can actually do, the sensitivity analysis, to see if our results change by using the emulator versus the real thing. But in practice, this exercise that we're about to go through is not something that can be done, just because, well, the reason we have an emulator in the first place is because evaluating a simulator is very expensive and very time intensive. So we can't just, we can't run it enough to do our sampling, because if we could, we wouldn't need an emulator. So now let's redefine our likelihood using the actual model instead of an emulator. So everything is the same, except now we don't have that additive form of the variance. We simply have just that noise variance, that baseline noise variance in the problem. And then we use the same prior distributions as before. We use the same prior distribution as before, and then use this posterior, define these posterior distributions. And then, just as before, we're going to use finish the same code to do all of the MCMC sampling. And so we're going to let that run for a second. So now that went fairly quickly. And then what we're going to do is plot these target posteriors against our emulator posterior and see how they line up with one another. So let's do a little bit of comparison. So on the left, we have the posteriors using the flat prior. On the right, we have the posteriors using the simulator. So these are more, or sorry, no, with the left we have flat prior, right we have peaked prior, and on both we have one with the simulator in blue and with the emulator in red. And so we see in the case of the flat prior, we see some deviation between the different posteriors. And so the rough shape of the distribution is mostly pretty well captured when we using the emulator versus the posterior, but we see that we're off by a little bit. And of course, that could be a consequence of having a small number of samples. Maybe if we draw a bunch more samples, they look closer. But we see already there's kind of some level of divergence between the two, but not anything like heinous. But there is some level of difference, and perhaps if it's a difference between not being able to do the problem at all and having a little bit different from the true posterior, then I would say that this is acceptable. And then what we see on the right side, we see that the two posteriors match up very, very well. And so you may be tempted in this case to say, okay, well, maybe then the peaked prior is better because it allows us to use the emulator without any sort of loss of accuracy. But I think that's not the right takeaway in this case. I think the probably the real answer is that in this case, the influence of the prior is so strong that the difference in the likelihood due to using the emulator or not doing it is almost, it kind of pales in comparison to the influence of the prior. So the prior has a outsized impact compared to the likelihood in this case, which is why you're seeing that the two posterior distributions are almost identical. So I guess one thing to summarize here is that your choice of prior can have a sizable impact on your conclusions that you make in your modeling. So always be wary of that, and give a lot of thought to the selection of priors. Don't just kind of have some automatic thing that you default to, or let it be just some fixed process. It should be something that prior distribution should be given consideration, except in cases where you have a bunch of data and then your price of your choice of prior has less of an impact. But especially in settings where your data is really limited, which often in physics these experiments can be really expensive to deal with. So you're going to have maybe a smaller amount of data. So you should really give a lot of thought to your prior, because it can this Bayesian paradigm, it gives us a lot of flexibility. It gives us a lot that we can do. It makes it really easy to make different types of images, because we're working with samples from like an empirical samples from your posterior distribution. It's really
Yeah, I think we just lost our speaker.
So let's give it a minute and assume that he is going to be able to get back online. And we've already heard from him, so he is. So let's just give a minute for Zoom to have. There we go. We can. Okay. You're muted. Beautiful.
Okay, I am back. Sorry about that. I don't know what happened there.
Back in business.
You're back in business. So what I was saying, the point I was making is that one critique of Bayesian methods is that your results are sensitive to this choice of prior distribution. The way I would respond to that is in any sort of data analysis, you have to choose some model. So there is some elements of subjective choice within any paradigm of data analysis. And so people like to focus on these priors, but you get a lot by being in this Bayesian paradigm. And I think importantly, of course, choosing a bad prior can work against you. But there's the added benefit of, if I'm in a setting where I have some prior knowledge and I know how things should look and might work, you're able to incorporate your prior knowledge of whatever problem you're working on into your modeling, which is a very helpful thing. And so that's what I've summarized. Bayesian inference is an extremely powerful tool that allows us to incorporate prior knowledge into into inference, into parameter estimation. And using emulators allows us to do it in a very effective way and to very effectively solve inverse problems in a flexible manner. So I think with that, I'll kind of summarize the main portion here, and then I'll stop. We have a couple minutes left for any sort of questions that anyone has. They're still lingering.
I'm not hearing any, and I don't see anybody typing.
Okay. Well, then I hope this has been informative for you all. I hope that you've taken at least something from it and have some practical ideas that might be helpful in your own research. And so thank you everyone for your time and attention. Really appreciate it.
Okay, thanks a lot. I think that was very, very helpful.
And that's a good place to close the session. We are gonna go ahead and, when we have the recording, we'll post the recording online, but it's gonna take a few hours because Zoom and YouTube process the video. Thanks, everybody.